start by thanking all the organizers, especially Samriddhi, for continuing this interesting meeting. Okay, so I'll talk about page entanglement dynamics in a very simple model. And so this is work done with Manas and Madhumita. So Madhumita is the person who did really some amazing numerics and analytic calculations, which I'll try to explain. Okay, so I'll kind of give some motivation, and it's related to this black hole information loss paradox. So let me give a very quick explanation of what this paradox is, as what I understand. Okay, so basically, so black hole is formed by, like matter collapses, I mean, because of gravitational attraction. And I mean, we expect that it's described by a pure wave function psi. What Hawking showed in 1975 is that even after a black hole forms, it can actually radiate. And what it radiates is thermal radiation at a temperature that depends only on the mass of the black hole. Okay, so independent of what goes in and so on, all that is forgotten. It just radiates at some like black body radiation with some temperature which depends only on mass. Okay, so eventually the black hole evaporates completely, nothing is there, and you have just pure thermal radiation. Okay, so then the question is like initially the black hole is in a pure state. There's a lot of information of what it's made of, and so on. While the final state is pure radiation, so where is all the information gone? Okay, so that's the information loss paradox. And another way of saying is that you started with a pure state, you end up with a mixed state. So there's loss of, it looks like there's violation of unitarity. Okay, so in all this paradox, entropy plays a important role. So what Hawking showed in his, so he did, I mean, for gravity, you don't have a quantum theory. Oh, it's already 2 minutes, okay. So what he showed using a semi-classical calculation is the entropy keeps increasing of the radiation. So then there was a very interesting work by Page who showed that actually if you look at the entanglement between the black hole and the radiation as it evaporates, then this curve has to be non-monotonic. Okay, so so this was another way of stating that there's a paradox. Okay, so there's an interesting article by Christian Mace which basically says that there's actually no paradox. Okay, and this is kind of interesting to read. Okay, so this is the summary of this. So so this is the Page curve. It's entanglement between the black hole and the environment as a function of time. What Page showed is that it has to follow something like this. It has to go up, but it has to go down eventually. And what Hawking showed is that if you look at the entropy of the radiation, it keeps increasing. Okay, so that's the paradox. Okay, so what we do is we look at a very toy model to kind of reproduce this kind of a Page curve in a model which roughly looks like a black hole evaporating. Okay, so so it's kind of motivated by like all this work by Calabresi and Cardy, who look at entanglement evolution in free fermion systems. And okay, so what I'll talk about is, so the system is this. Okay, so you have a lattice, 1D lattice, and initially, so this is what I will call the system, and this is what is the reservoir. So this is a finite box of n sites, and initially it's completely filled with, it's a filled fermionic lattice. And this side is completely empty, okay. And then there's some, so it's all uniform hopping elements, and there's some defect out here. So this hopping element is different, but everywhere it's the same, okay. So it's like initially it's a closed box, and at some point I open this box, and the gas just expands, right? And I calculate the entanglement between this, whatever is remaining here, and whatever escapes to this part. Okay, so what I'll present is exact results from, so you can do this entanglement calculation exactly from microscopic numerical calculations. And we can also compute this using a sort of semi-classical approach of generalized hydrodynamics. Okay, and the main, one of the main results is that we find that these two approaches, there's a remarkable agreement. Okay, so this is the model I already said is just some hopping Hamiltonian, and there's a defect at this site. And we study different kinds of defects, but I won't go into that. Okay, because it's free fermions, it turns out that it's very easy to do calculations even of entanglement entropy, which is normally difficult. So basically one has to look at 2-point correlation matrix. So the system is always in a pure state, and you can compute this 2-point correlation matrix. And this correlation matrix evolves in a very simple way. Okay. And from this correlation matrix, you can compute various things like what is the density profile. So initially it's a step profile, how does it evolve? What is the total number of particles remaining at any time? What is the fluctuation in this number, and so on. And then you can also compute things like the entanglement entropy. Again, for this non-interacting system, there's a and if you focus on Gaussian states, then there's a simple calculation. Just using the correlation matrix, you can actually compute the entanglement entropy by doing diagonalizing this correlation matrix on the subsystem. Okay, so so that's the microscopic description, and the hydrodynamic description is basically you think of this as a gas of non-interacting fermions, right? So you can write a single particle phase space density, which tells you what is the number of fermions in some local region with momentum k, and this will kind of satisfy this kind of a Euler equation, or you can think of it as a Boltzmann equation, basically with no collision terms, right? Okay, so so initially you start with some phase space distribution at t equal to 0 and see how it evolves. Okay, so and it turns out that given this phase space distribution, there's some way you can also compute entropy by just assuming that the system is in kind of in local equilibrium state. Okay, so locally, if it's in a equilibrium state with some Fermi distribution, then you just add up all the entropies of this local equilibrium state and compute the entropy. Okay, so this is the hydrodynamic entropy that we compute. And okay, so this thing is something we can actually analytically compute the hydrodynamic evolution of the phase space density. And I'll just show you the comparison of what we get from hydrodynamics and what we get from exact results. Okay, so this is the density profile, how it evolves. So initially it's a step profile, and then with time it evolves in some way, and you see exact agreement between the hydrodynamics and numerics. Okay. And this is the entanglement entropy. So this is the main result. So I show you three. One is the exact microscopic entanglement entropy, this dotted line, and it follows kind of what you expect from the page curve, right? It goes up and goes down. Then there is a hydrodynamic calculation of the entropy of the reservoir. Okay, so it's like the radiation entropy that Hawking calculated, and this keeps increasing as what is found in the black hole problem. Okay. And then you can calculate the entropy, the hydrodynamic entropy of the system, and this you find that it actually follows what you compute, the entanglement entropy that you compute from microscopics. Okay. So this is the really amazing part. I mean, that what you calculate from semi-classical calculation actually matches exactly with the microscopic calculation. Okay, so I think since there's no time, I won't show. We looked at their interesting finite size effects, and okay, there's an interesting relation between entanglement entropy and full counting statistics, which also we can verify in this system. And okay, so I'll just stop with the conclusions. That's just like we studied three kinds of defects. One is a conformal defect, which is it's a special kind of putting the hopping and on-site defects, so that what's special about the conformal defect is the transmission coefficient is independent of what wave vector you look at. That's a statement.
Very nice talk. How do we know that the black hole is initially in a pure state? What guarantees that?
I mean, that's you expect the world to be in a pure state, universe to be in a pure state.
Okay, let us thank the speaker.